Hello everybody, I'm going to solve problem 1.15 from my physics textbook. The problem is estimate the average temperature of the air inside a hot air balloon, see figure 1.1. Assume that the total mass of the unfilled balloon and payload is 500 kilograms. And what is the mass of the air inside the balloon? Now, the first thing I'm going to do is draw a picture of it so I can get an idea for what's going on. So I'm going to draw me a little hot air balloon. There we go. Now I'm going to start making some assumptions about this hot air balloon. I'm going to assume that the air inside it is an ideal gas. I'm going to also assume that that gas is at standard temperature and pressure. I'm also going to assume that this balloon exerts a constant pressure, that the pressure doesn't change throughout the balloon doesn't have a change in pressure. I'm also going to assume that my system is the balloon, and the environment is everything else. So let's put in these assumptions. So that means the pressure here is 1 atmosphere. The pressure here is 1 atmosphere. The temperature outside is around 300 Kelvin. Don't know what the temperature is inside because this is the gas here, although are the same, is at different densities. I'm also going to put the force of gravity here on the payload, big mg, and I'm going to say the mass of the air is little mg. Now, in order for this balloon to float, it has to have buoyancy, so I'm also going to put the force of buoyancy on this balloon as well. Now, I can also estimate this volume from the picture. This volume I'm going to assume to be roughly spherical shape. So I'm going to say volume is a sphere. And I'm going to show that, and from the picture I can get a scale of what it is. And so I have determined that this balloon, from in this picture I'm basing off, it has a diameter of roughly 18 meters. Now, in order to estimate the temperature, I'm going to say it's going to be between 300 Kelvin and 400 Kelvin, because 400 Kelvin is the temperature cap most balloonists have in order to preserve the material. So that's another assumption I'm going to make, is my temp cap. And so now with this, I can start to figure out what the mass of the air is inside the balloon, because the sum of the forces has to be 0. And so that means that the force of the buoyancy must minus this force of gravity. Now, little mg can be included with the force of the buoyancy because that's what's actually keeping the balloon up. So its force of the buoyancy is the density times volume times g. Now, since this is equal and I have two buoyancies to work out, remember it's the outside air and the inside air, so I can say that all the forces is the density of the outside air times volume times g minus the density of the inside air times volume times g minus big mg. Now, solving for not solving for m, I can times the inside density by this volume to get the mass of the inside air times g minus big mg. Solving for m, I get m equals the density of the outside times volume minus big M, because these g's will cancel. And so that is equal to 1.225 kilograms per meter cubed times 3,053, because since I'm assuming this is a sphere, meters cubed, I'm assuming that it falls to 4/3 times pi times r cubed. And so this is what that, and so this is the volume minus that 500 kilograms, which gives you the mass of the inside air as 3,240.7 kilograms. Now that I have this mass, I can also now figure out what the temperature is, what the actual temperature is instead of this range. So if I say that working with the ideal gas law, PV equals NKT, and if I equals solve for V, I can get N times V times K times T. Now this is the number density. So all I need to do is just times mass, and I get the inside density in order to help solve for this equation. So if I just times all this by mass, I get T times K times the density equals MP. So that means I have T equals MP over K density. Now this density is the density of the inside gas. So which I have found, I can find by dividing by this mass divided by the volume. So temperature is equal to this mass, but I don't know what this mass is because that's the mass of the individual gas particles. So I'm going to assume that said gas is made mostly of just N2, so nitrogen. So that would be 14 grams per mole times 1 mole over 6.02 times 10 to the 23rd times 1 kilogram divided by 1,000 grams. Get rid of the grams, moles, mostly maybe just kilograms. And so that gives me 2.3 times 10 to the 23rd. However, sorry, not 23, 26 kilograms. However, it's N2, so I need to times this by 2, which gives me 4.6 times 10 to the 26 kilograms. So now I can solve for temperature. So I get 4.6 times 10 to the 26 kilograms times 1.013 times 10 to the 5th newtons per meter squared all over this density, which is 3,240.7 kilograms divided by this mass, which is 3,053.6 meters cubed. Sorry if you couldn't see that over here. My pen doesn't pick up things sometimes. Times 1.381 joules per Kelvin. Now, doing the calculation for this gives me a temperature of about 321.5 Kelvin, which fits perfectly in my range. So this is a plausible temperature, and the units check out for both of these, for both the mass and the temperature. So thank you. So that means that these two are perfectly valid and not valid, but plausible answers for this problem. Thank you for joining me. See you next week.